All right, so we're kicking off section 8.2 right here. And before we jump into that, I want to remind you guys of something I showed you last chapter. And that is talking just about how the book structures our next couple of units here, which I think is really helpful because it's pretty consistent in the approach. The first section of the chapter in 8.1, we wrapped our heads around a new concept. Last chapter was sampling distributions. This chapter is the idea of a confidence interval. Now, what we're going to do in section 8.2 is we're going to learn how that concept, how confidence intervals can be applied to problems with P in them, our proportion symbol. And then in 8.3, we're going to learn how confidence intervals can be applied to problems with mu in them. So those conditions and all that crazy stuff we learned last chapter is going to come back into play. Those formulas we talked about, we're going to see all of that again in this unit and in the following chapters as well. So let's get to it. There are going to be three conditions that you'll be expected to check in problems related to confidence intervals. And later on in the year, when we learn about significance testing, the same conditions basically apply there as well. These should look familiar to you guys because I believe at this point we've talked about all three of these in some fashion. The first condition is the easiest, and that is that your data needs to come from a simple random sample. Remember that I told you earlier on in this chapter that the only type of sampling we will look at for making confidence intervals is an SRS. So when you do a problem on a confidence interval, or whatever kind of testing thing I'm making you do, you need to acknowledge when you're setting up like your little solution that your data came from a random sample. Okay, so it needs to be a simple random sample that your data comes from. If you don't have that, you risk running into bias in your results. So what I'll do next to each of these is I'll put like a little reason for why we check them. So this ensures there is no bias from sampling. It doesn't prevent things like wording bias. Like if I make my question very slanted one way, even if I get an SRS, my data could still be biased. But it basically removes the possibility of sampling bias in your results. The second condition we're going to check, we've seen a whole bunch. It's that 10% condition. And see if you can remember as I'm writing this down, what you need to check or why we check the 10% condition. What do we need to check the 10% condition before we calculate? And you should maybe remember that what the 10% condition does is it lets us find our standard deviation. We need to do it before we do our standard deviation formula. The reason for that is it ensures that trials or selections are approximately independent of one another. And the reason we do that is it lets us find our standard deviations. So right now, this is still like conditions. There's a lot going on right here, and it'll be hard to remember. You're going to see this again and again and again, like the next 3 or 4 chapters. So you're going to get pretty good at knowing why we check each of these things. And our third condition, which we introduced last chapter, was the large counts condition. And see if you can remember as I'm writing this down what the large counts condition actually tells us and why we check it. So what we actually have to do for the large counts, it was the n times p and n times 1 minus p that are greater than or equal to 10. Greater than or equal to 10. This is what you actually have to check when you do this. And if you remember, we did like the little Reese's Pieces applet. The reason we check that is basically to make sure that we don't get too close to the edges of 0 and 1 in our normal distribution. So our graph doesn't get cut off and end up skewed. Because if the center is like really, really low, you'll have a little cutoff right there. We did a whole thing on that last chapter. So the reason we check the large counts condition is to ensure that the sampling distribution of, in these problems, like I would say X bar if we were doing a mean problem, but this is P problem territory. So it's the sampling distribution of P hats that is approximately normal. And we need it to be approximately normal so we can do all those normal CDF calculations that you guys are used to. So these are our three conditions and why we check each of our conditions. Now, I'm going to go ahead and address this now, but it comes up again on like the next slide as well. Here's a little tiny mini curveball on this last condition here with large counts. When you make a confidence interval, you always make an interval on a parameter, never on a statistic. So if I want to make an interval, I'm going to make an interval to help me predict P, real P. I'm not going to make an interval to help me predict P hat because P hat is just literally what I got from my sample. If I wanted P hat, I would take a sample and I would look at P hat. I wouldn't have to make an interval. So anytime you make an interval, you make it for the parameter, which is the thing you don't know. So what's weird about this is in a P problem, I would be making an interval to try to figure out real P. That's what I would be looking for. But this condition right here makes me know real P. I can't check this condition here if I don't have P because that's what I'm trying to find in the first place. So it's like a little weird right there. So what you actually do to account for this, or what we do to fix it, instead of plugging in P, which we don't know, it's the whole point of the problem is to find P, we're going to plug in P hat instead of P. So when you check your large counts in this chapter, we sub in P hat in place of the P because we can't use P since we don't know it. Okay? So I sub in the P hat, and that is an okay move. I'm not going to get into the specifics of why that's all right, why we can just make that substitution, but it has to do with the fact that P hat is approximately normal. So that is a totally adequate substitution we're allowed to make. What happens if any of these conditions are violated? Well, our confidence interval won't work as advertised. So if I take lots and lots of samples, if I'm doing a 95% confidence interval, if I take lots and lots and lots of different samples, make an interval for each one, about 95% of those intervals should catch the right answer. Well, if I violate a condition, what that's going to do is it's going to mess with my success rate. So instead of getting like that 95% like I'm looking for, I may be lower than that. I may get 84, 92, something like that. Hard to say exactly what will happen just off the top of your head if you change something, but just know that we need to meet these conditions or it messes with our success rate in problems. So let's keep it going here. And this next page is going to tie into what I was just talking about with P versus P hats. So you have to remember, we learned about P hats last chapter. And the way that that worked, that was a sweet number line. We know that the graph of P hats was centered at real P. The mean of the sampling distribution of P hat was actual P right here. So the graph centers right there. That was going to be the mean. And if you recall, the formula for the standard deviation was equal to, so the standard deviation of the sampling distribution of P hat was going to be a formula, which is on your sheet, which was P1 minus P over N. It was this guy right here. We saw that last chapter. But we run into the same issue here that we did in the last slide. And that's the fact that I'm trying to figure out P. I want to know P. That's the whole point of doing all this fancy math. Well, if I don't know P, if that's what I'm looking for, how could I ever do this setup right here? I couldn't. So what we do with this problem is we replace those P's in the formula with P hats. So this, when we sub in P hat, changes it. Instead of the standard deviation uses real P. We're not going to have access to that. We're going to instead find what's called the standard error for P hat, S of P hat right here. And it's going to be the same formula, but with P hats in place of the P's. Now, again, I'm not getting too into the detailed proof-based math behind this, but why are you allowed to do that? Plug in P hat for P. Well, we know that P hat's distribution is approximately normal, so that works out okay. So we replace our P's, turn them into P hats, and we're good to go. Will these formulas be on the AP formula sheet? Yes, mostly. So let me show you what I mean by that. On your formula sheet, I mentioned there was a little breakdown confidence interval is statistic plus or minus critical value times standard error of statistic. We talked about that a little bit last time. That's on the first page of your formula sheet, just that general setup. And if you scroll to the second page of the sheet, we've used this last chapter in chapter 7. They have on this paper right here the parameters, your mean and your standard deviation with actual p's, and then they have the standard error over here on the right side with p hats plugged in instead. So yes, the pieces are on the sheet right there. If you make an actual interval, you'll have to put it all together, and I'll show you how that works. So, will these formulas be on the sheet? Yes, mostly. All right, so let's keep it going. If you recall, or if I just reviewed it again 5 seconds ago, but from last lesson, what we talked about is if you are going to make a confidence interval, you start with your points estimates. And the point estimate that we use is going to be our statistic. So you start out with a point estimate, which is the statistic. It's what you get from your sample. After you get your starting point, that was me with my sign on from a few lessons ago. What we do is we add or subtract that margin of error that goes from middle to edge. And then what I did in the last video is I broke that margin of error into 2 pieces. There was what's called a critical value, and then we multiplied by the standard deviation of our test statistic. But unfortunately, as we just uncovered, we can't do standard deviation because it used the p's instead of the p hats. So instead of doing that, we just use the standard error of our test statistic. Standard error instead of standard deviation, because we would have p hat and not p. So this is going to be our basic breakdown for how you make a confidence interval. So that's our basic setup for how you write a confidence interval. Now what we're going to do is we're going to take this formula, kind of little setup right here, and turn it into an actual formula with variables in it related to problems for p. So you start a problem by using the statistic version of what you're looking for. So in my example with the texting, I had mu that I was trying to estimate. I used x bar, my sample mean. Well, in this problem, we want to estimate p, a proportion. So our statistic is going to be a p hat, our sample proportion. We are going to add or subtract a critical value. And the way I explained critical value last video was it's basically counting how many standard deviations you want to go from center, and that affects what percentage of the different values for p hat in this case will fall within that range. So the critical value is going to actually have its own symbol. The symbol for a critical value in these problems is going to be a z, like a normal distribution z, with a star on it. So z star stands for a critical value, and I'll show you how you calculate those in just a minute. So we have our statistic right here, p hat plus or minus a critical value times the standard error. And remember the way that works for standard deviation would be p1 minus p over n, but standard error is going to plug in hats on those p's because we don't know actual p. So this is going to be our formula right here for making a confidence interval on a p problem. Last section, they just gave us the interval and they said, hey, interpret this for me, use it for me. But this is how we'll actually build the interval for ourselves on a p problem. And we'll practice that as we go on through our notes here. So the first thing I want to do with you guys is talk about the z star and how you actually calculate one of these things. Remember that the idea was when you look at this problem, picture it like a number line. On a number line, last time I had for my center a mu. This time though, we're in p problem territory. So we have real p. The sampling distribution of p hat. P hat's graph, that was a bad right side of the graph right there. P hat's graph is approximately normal as long as that large counts np, n1 minus p is satisfied. So if we were to go one standard deviation each way from the middle, we would expect 68% of our data points to fall in that range. If we were to go 2 standard deviations, we would expect 95% of the data points because it's approximately normal, and that's what the normal distribution does. But when we talk about confidence intervals, you all won't always use one of those nice numbers, like a 68, 95 type situation. Like here I have an 80% confidence interval. So what I want to do is figure out the boundaries where 80% of the values for p hat are going to lie within. In order to do that, the area of this middle part of my picture is a point 80. I just have to do a little quick math right here. What that does is that makes this tail 10%, and it makes this tail 10% as well. For an 80% confidence interval, I want 80% of my different p hats to be within the range. Well, from the middle there, from p, that's going to be 80% of my area. So what I need to do, this is a throwback to chapter 2 here. I need to look up my inverse normal command. So I would do second distributions, this menu right here. I would choose inverse normal. And if you have a newer calculator, you might have an option for a center area where you can just put 0.8 and it'll tell you the answer. I don't have that, so it always does left area when you don't have a choice. My left area is a 0.10 area from the left side until I hit this mark right here. I'm going to leave it standard normal, mean 0, standard deviation 1. And when I do that, it's going to tell me negative 1.28 I'll go with. So this mark right here is negative 1.28, and that would make this mark positive 1.28. So if you go 1.28 standard deviations each way, you're going to have 80% of your data points within those boundaries. So what that tells us is that our critical value for this problem, we would want to go 1.28 standard deviations. It gave me the negative version of the number, but for a critical value, you just always put the positive version of that number. It comes right after a plus or minus sign anyway, plus or minus z star. So if you used a negative, it would just reverse it. It's the same thing, okay? So pick the positive version of the number. This should go a little faster for this next one here. You would do the same exact setup. It's always the same setup. This time though, I want 90% confidence. So this area is 90%. I would have a 0.05 here and here. So this time when I do my inverse normal, I would want to do it with a left area of 0.05 instead. So I would do inverse normal, left area 0.05, mean 0, standard deviation 1. This is one of 2 values for the critical values I have memorized. It's like 1.645. And you will see negative 1.645 if you round it right there. Okay? So what I would do is I would write down, just drop the negative sign on it. You have z star equals, it's about 1.6. If you just did 1.64, that would be fine, but I'm going to go 1.645. When I took all my statistics classes in college and master's degree and whatnot, we use 90 and 95 a lot. So I have those two just memorized from frequent use. You may do that as well. You may not care to. It's fine. You can just do an easy inverse normal. Try out this 95% on your own and figure out, mimic my setup right here. The answer you should get when you do the 95% confidence interval is z equals 1.96. Now, you may look at that and be like, wait a minute, I thought 2 standard deviations was 95%. Well, that rule with the 2 standard deviations is a little bit rounded. It's a little bit of an approximation there. To get exactly 95%, you should be actually at 1.96 standard deviations away. So finding a critical value is just doing an inverse normal. Maybe I'll write inverse normal up top so you guys have it to look at later, but it's really not that bad to do at all. So that's how you find a critical value here. And hopefully that makes sense with the standard deviation thing that we were talking about. This is just restating what we've already talked about in this video. Here's our formula for a 1 sample z interval for a population proportion. It's kind of a mouthful right there. Basically, what this means is it's a CI for P. It's 1 proportion that we're basically doing an interval on, as opposed to 2 proportions, which we'll learn about later on in chapter 10. So this formula we already talked about. It's the exact same thing you saw earlier. This slide has nothing new for you guys. It's just restating what we've already covered. So you've got it nicely typed out there. So we're going to go ahead and work through a big example here to make sure that this is all making sense and kind of tie stuff together here. So we're in an AP Stats class, and we want to estimate the percent of pennies in circulation that are more than 10 years old. This is what we care about in the problem. Proportion of pennies that are more than 10 years old. So we take a random sample of, it looks like 102 pennies, and we find that 57 out of 102 are more than 10 years old. So identify the population and the parameter of interest. Well, my population in this problem is all pennies in circulation. We're trying to figure out what's going on about all pennies in circulation. You could make the argument that the population is actually all pennies in circulation in St. Louis or just our area, because we're not picking random pennies from other parts of the country. But the goal is whatever we're random sampling from. We're trying to apply our results to as many pennies as possible. The parameter of interest, our parameter in a problem like this, when they talk about proportion, that is a percentage, which is a P problem. So our parameter is going to be P, which is the true proportion of pennies in circulation. And we care about pennies that are greater than 10 years old. That's just what we care about in the problem. So we define our parameter, important step that we'll always have to do. Then it says to check the conditions for calculating a confidence interval for the parameter. There are 3 conditions, and you have to memorize them and know what they are. First condition was a simple random sample. So this problem says, oh yeah, it's a random sample of 102 pennies. Check. There will not be a situation where they give you this big old problem and it's like, trick question, you couldn't do it, unless they were like purposely testing for that, and then they would ask you like follow-up questions. But it's not going to be like, oh yeah, make me an interval, do this whole thing, but ooh, it wasn't a random sample, gotcha. They're not going to do that to you, but you still need to check the condition and verify, yes, this was a random sample. What this is basically doing is training you guys where, like, if you were to do statistics in your own life at some point and make an interval for whatever, we do a big end of semester project where you'll actually get to do this. You want to make sure you have it in your head that, oh yeah, I need to do a random sample. The second condition is the 10% condition. So 102 is definitely less than 10% of pennies in circulation. Check. And then the third condition takes a little more space. It's the large counts condition. I'll do that up here where I have more room. And remember what large counts says. Large counts says you do n times p and n times 1 minus p, and those both have to be at least 10, which shows that your distribution, sampling distribution, is approximately normal. But we don't know p, because that's what we're doing. That's the whole point of the problem. So we use p hat instead. In general, good tip for the AP test right here, you guys shouldn't write down stuff with symbols like this. Don't do this on your test papers, because let's say you forgot the hat and you accidentally wrote n times p, n times 1 minus p. They will take off if you use the wrong symbol. When you meant p hat but you say p, that costs you credits. So it's better just to get in the habit of not even writing this part of it and just write it with the numbers plugged in. Well, my n is 102, and my p hat, what is that? Well, it's what I got in the study, which was 57 out of 102. I could make that a decimal, but it's actually easier to leave as a fraction because your 102s are just going to cancel, and you get 57. That's totally greater than or equal to 10, so that's cool. But I also have to check it the other way. N times 1 minus p. So what is that? I think that's 45. Pretty sure it's 45. If I'm wrong on the math, whatever it is, it's greater than 10. So we're good there. So this tells us that the distribution is approximately normal. What is approximately normal? Well, it's the sampling distribution of p hat. It's p hat's graph. But if you're going to forget that on a test, just say, oh yeah, approximately normal. And that should be good enough. You've at least acknowledged that the distribution should be approximately normal. If you said actually normal, that might cost you credits, so don't do that. Now we have to actually make our interval. So we're taking all of these pieces from the last couple lessons and we're putting them together to make our own confidence interval. So the formula starts out with a p hat. Again, don't write the symbols yourself. It's better just to go to stuff plugged in. Our p hat in this problem is 57 out of 102. And you could make this a decimal. There's nothing wrong with that. It may honestly be easier to go decimal here. So I'm going to go ahead. You know what? I'll just type it in. 57 out of 102 is 0.5588. Just don't chop your decimal too soon if you do go the decimal route. So 0.5588 plus or minus. Time for a critical value, z star. Well, I don't know a 99%, so I have to do an inverse normal. When I do my inverse normal, if I have 99% in the middle, that makes this not even 1%, 0.005. So I would do 0.005 for my area, and that is 2.576 or 2.58, depending on how you round it. So I'm going to go 2.58. The AP test is pretty forgiving about rounding. If you make this 2.57, 2.58, it's cool. As long as you show your work, you're going to be fine. Then I have to do my standard deviation formula with that 0.58 whatever decimal, 558, plugged in. Because it goes p hat 1 minus p hats. And then I have to divide by n. So what I did for this is I did 0.5588, 1 minus that, and then it's over n, which is 102. And that was a point, I should have written that up above. That's 0.0491-ish. Okay. So the next thing I'm going to do is I'm going to clean up my little setup right here. I'm going to take these guys and I'm going to multiply them together. So I'm going to do my 2.58 decimal. And it's always a good idea to pull the full decimal from your calculator when you set this up. So grab the entire decimal, which I'm sure you guys know how to do here. When I did that, I got 0.5588 still. Didn't do anything with that yet. Plus or minus. This side ends up being 0.1266. So that's your margin of error. The margin of error is the critical value times your standard error. So that whole green bubble, margin of error, about 12%. Not great for a study. Usually, like I said, when you do a survey, 3 or 4% is what you're looking for. But we pulled 102 pennies, which isn't that much. So we have a higher margin of error as a result. Then all I'm going to do is add and subtract that 0.1266. I'm just doing plus or minus. Easy math there. My low end is 0.4322. That was from doing a minus. And then my high end, if I go back and I add that, is 0.6854. So we have to interpret this interval. I will pause to actually write it to save you the trouble of watching me write it, but let's talk about what this says. We practiced our script in the last section. This is where we're going to say that we are 99% confident that the true proportion of pennies in circulation that are greater than 10 years old is somewhere between 43% and 68%. 43 to 68% is a pretty big range, but like I said, our sample wasn't that large. If we wanted to trim that down, we have two options. One option is raise that sample size, so take more than 102 pennies. The other option, that's a 99% interval. I could go with like a 95 or a 90 or something like that. So I'm going to pause, I'm going to write the answer up there for you, and I'm going to come back with a few other comments about that 95 and 90. All right, so I'm back. I have the solution written up over here, and I added a lot since I paused this. So copy down that and have the nice written up script for your answer. But what I want to do a little bit is talk about the difference between a 95, 99, 90, and talk about what's most commonly used real fast. So make sure you have the little script written down so you can focus on this last part. When you change the critical value, when you change the confidence level, when I went from 99 to 95 to 90, all that's going to change in my purple formula over here, the only thing that changes is this critical value right here. This guy is controlled by your percentage right there because it tells you how many standard deviations from the middle to go to get this percent of values. So if you basically say, oh, I want 90 or I want 95, same exact data sample, still those 102 pennies, didn't change anything about what I did in real life or in my penny problem. All that changed is I'm like, ooh, my confidence level is going to switch. Now you may ask yourself, like, what is the best confidence level? Wouldn't you want to be right like all the time and almost all the time and use a 99% confidence interval? Well, in my 99% problem, my margin of error on this problem was about 12%, plus or minus 12%. When I switched it to a 95, that brought it down to like a 9%. So it cut off, what is that, 25%? It cut off quite a bit of your margin of error right there. To get that extra 4% certainty right here, although certainty isn't a good way of putting it, but to get that extra 4% level of confidence, you have to go a whole extra standard deviation in your picture right here to get 3 standard deviations almost away. So what happens is as you increase your confidence, you go from 68 to 95 to 99.7 to 99.9, you have to get progressively wider and wider and wider to capture that area because there's so little area left in the tails. So basically, getting that far out to the 99s and stuff isn't really worth it for the amount that it balloons up your margin of error. You would guess maybe 99% is the most popular margin of error, or sorry, most popular confidence level, but it's not. 95, I would say, is kind of like the gold standard that you see the most frequently. Sometimes 99, sometimes 90, but I would say 95 is definitely the most popular. It's kind of the sweet spot between like, I want to be right a lot, but I also don't want my interval to be ridiculously wide. Because jumping to that 99% makes you go quite a lot farther to get that much more area. So that's just a little, the more you know, kind of a thing. All right, last thing is I need to talk about this last question. Is it plausible that more than 60% of all pennies in circulation are more than 10 years old? Now, the word I need to make sure we talk about here is that word plausible. The word plausible is different than the word possible, is different than the word convincing evidence. So, if I say something is plausible, what I mean is basically, is it realistic? Could it be? It's possible that as I'm filming this video right now, like an asteroid is going to come through my roof and just like destroy my house and I'll be gone. It's possible, sure, theoretically, but it's not plausible. It's probably not going to happen. It's not realistic to assume that will occur. So the word plausible kind of conveys a sense of like, is it realistic? Is it realistic that it could be 60% of pennies that are more than 10 years old, at least 60% of pennies? Well, yeah, there are numbers above 60% in my little interval right here, no matter which one I use. So that tells me, you know what? Like, yeah, it's plausible. It totally could be more than 60. But if I said, is there convincing evidence? The answer is more than 60. If I just tweaked that wording a little bit, the answer to that would be no, there's not convincing evidence. There are numbers that are also below 60% in this interval. So we couldn't say for sure if it's above 60 or below 60. So is it plausible? Sure, it could be. But is it convincing? No, it's not. That's a difference that you guys have to be very careful about when you're doing these. So plausible, yes. Convincing, no. So as you're looking at these problems here, you have to make your decisions based on just thinking them through and looking at your interval of the possibilities. It doesn't matter if your interval barely covers whatever number you're talking about. If it's in the interval, you still have to like account for it. So it doesn't matter if my interval went from like 0.59 to 0.75 or something like that. If I said, is there convincing evidence that it's at least 60%? Well, I mean, yeah, more of the numbers are above 60 than below. But if there's anything in the interval that disagrees, you can't be convinced. It's not strong enough evidence to push you kind of over the edge. So yeah, that's how you make a confidence interval on a proportion.